Afternoon, everyone. Basically, we are on the afternoon. So this is Ahmed Assad, and I'm actually a university professor at the Australian University in Kuwait. I'm happy to show you some of the work that we have been doing in our group. So this is basically the agenda that I'll be going through today. No, that's better. Okay, so I am talking about yes. So I'm talking basically about bridges. And as we all know, bridges are basically kind of a critical infrastructure systems that is responsible basically to secure the mobility of both people and also commodities, ensuring a proper functioning or continuous functioning of those critical systems is of paramount importance, specifically after hazards, because they basically facilitate the firefighting and other rescue activities. Now, despite these importances, there are so many challenges that disrupt this continuous functionality, and we need actually to come up with a kind of innovative way to manage the bridges. That's what we call the bridge management system. And in a nutshell, or the simplest sense, the bridge management system is basically a series of 3 steps. The first one is basically trying to assess the condition of your bridge, and then try to estimate or to model the deterioration behavior over time, which will be used as an input to come up with a plan, maintenance and rehabilitation plan. So today, my presentation would like actually the first part, which is basically about the condition assessment. I'll be talking about condition assessment. Now, why I'm talking about condition assessment of bridges and specifically about cracks in bridges, because there are different ways of doing this. Previously, people would actually, it's still the most dominant approach, which is basically the visual inspection. You would dispatch a maintenance team that would go and visually inspect the bridge of interest, and they will have to report what they come up with. Now, the problem with this approach is that they are subjective. Obviously, they are time-consuming, very labor-intensive, and in many cases, they are hazardous, specifically when you require the personnel to reach some tight or very high spaces. Then people have tried to use some of the equipment like GPR, thermography, and other types of equipment. Now, despite reporting some good results, there are 2 main drawbacks of these equipment. Specifically, they are of a high capital cost. You need a high capital cost to run them, and you need a kind of expert for the interpretation of the results. So they decided, you know what, let's go to image processing. And image processing was a kind of a promising technique or tool because they were able to detect the cracks with a very high accuracy. The only shortcoming with the image processing is that you need a kind of a manual feature extraction, because there are basically 2 types, either the edge detection or the visual extraction. And in both cases, you have to do some kind of manual feature engineering. And also they are highly sensitive, as our chair just said, they are sensitive to the environment. So if the image quality was not clear because of whatever the conditions, they might yield a kind of reduced results. So people decided to use a kind of the deep convolutional networks, which is a kind of an extension. Let me just grab another pointer here. This is a kind of an extension to the classic image processing by using the deep convolutional networks. And the good part about this is that they can learn automatically from images. So they can acquire the feature extract, they can acquire and extract the feature needed for the detection. They can do the feature engineering automatically without the need for a manual or an expert interferences. Now, when it comes to computer vision or the application of deep convolutional networks, deep convolutional neural network, DCNNs, this is a kind of telling the story of how did it start over time. You have a kind of 4 different tasks. So at the timeline, they only first begin with a kind of the classification. So this is happening at the image level. Is there a crack or not a crack? That was the beginning. And then with time, they try to move on and they come up with a kind of we call the object detection. So at the beginning here, we were at the image level, then we moved to the object level. Is there a crack and where is the crack? We're trying to bound it within a bounding box. The next step would be about the segmentation. So here we're talking about the pixel level. So we're trying to classify each pixel, whether it is in a background or it's a crack. But the semantic segmentation would fail to distinguish individual cracks themselves. And that's what we're trying to implement here is the instance segmentation, because In cracks, segmentation, or generally the condition assessment, we're not only interested whether there is a defect or not. In fact, we'd like to know what is the severity of the defect so we can plan our maintenance and rehabilitation plans accordingly. So there's where instance segmentation play a role. It can actually give you the kind of dimensions, width, length, and also the orientation or the direction of individual cracks. So they don't just get a class for a crack, they have specific classes for each crack, which will obviously enable the severity assessment and then the maintenance rehabilitation techniques. So that was actually our objectives. We would like to develop a kind of a novel, autonomous, real-time detection of cracks and bridges. And to do that, we have first to come up with a database because, as usual, there's a kind of scarcity when it comes to the data in this field. And then we have trained and validated two different detectors. One, a single detector, single stage detector, and a double stage detectors to compare their respective capabilities. And yeah, that was actually the methodology. So the first step was about the data acquisition. We wanted to build our own databases. So we have actually consulted some of the available online sources, and we have done our own survey using our drones and other UAVs. We were tackling some targeted surveys, some targeted bridges in Kuwait, trying to capture their cracks. And we built up a kind of databases. That's our database. The next step would be trying to annotate those effects, and as you can see, we are not having a bounding box, and instead, we're going to highlight the exact area of the crack, because that's what we are actually interested in. We are not talking about crack detection, it's crack detection and severity assessment. The next step would basically be to split, obviously, the data as you usually know. This is the common split training, validation, testing. The training data set themselves, we have to implement some, or we have to apply some data augmentation techniques for them. On one hand, we wanted to enrich the variety of our data set, and we also wanted to mimic real-life conditions. So we have applied here, for example, some rotations, because we know that we are taking this using drones. The drone could be tilted a little bit or vibrated, so the cracks may not be as accurate or as straight. We have also changed the brightness plus or minus 15% just to come up with the different illumination conditions, and we applied some blur and noisy to the system. We have applied two different types of, we developed two different types of detectors. The first one is the single stage detector and the two-stage detectors. The main difference between them is that in the two-stage detectors, we start with a regional proposal where you, okay, I'm expecting that the crack could be there, and then they go and classify each pixel. While in the one-stage detectors, they can give you a probabilistic class estimation for each pixel directly without the need for the regional proposal. So this is a bit faster, but it comes with a little bit of compromise in the accuracy. This is a kind of the results of, okay, I have to also to say in the single stage detectors, we have tested different models, including the different variation of YOLOv11, V19. Well, when I wrote this paper at the beginning, the YOLOv11 was the most recent one, but now we have 12 and 13, just actually a few months ago released. And in these two-stage detectors, we have two different ResNet and faster networks. This is one of the examples, as you can see here. This is basically the results of the training and validation of only the YOLOv8. Two conclusions could be drawn here. The first one is that we have a kind of a decline, stable decline, which means that our model is successful learning. And also we're reaching a lower value of 0.4 or less, which means that the model has successfully acquired the complex features needed to detect the cracks. This is a comparison between the single stage versus two-stage detectors. Obviously, the two-stage detectors would definitely tend to, generally, tend to achieve a little bit higher, but that would come with a lot of cost. I mean, both the computational cost, this is the number of parameters we're using here in millions, and this is the inference time. So out of all, the YOLOv11 actually was the one that's achieved a kind of a balance, a trade-off between the accuracy and also the inference time with a kind of comparable number of parameters. Sorry, this is basically the recall precision curve. You know this, as you have more 90 degrees over here, that means you're able to predict the classes perfectly, because this is very important actually in infrastructure management. You don't want to miss any crack on one hand. On the second hand, you want to reduce the number of forced cracks, because each time you have a forced crack, that means you're dispatching the maintenance team for nothing. These are just some examples of the result we have continued, and I need to finish now. So Basically, this is what we're trying to achieve here, trying to compare two different types of detectors for crack detection, more importantly for the segmentation. A second part that I don't have actually time to present here is basically about the crack severity when we went down to analyze or trying to estimate the pixel area of the cracks. So that's it for now. I yield the floor for any questions, if any.